When studying probability, it will be helpful to use set notation for describing events. It's convenient to think of a set as a list of elements where the order of the elements in the list doesn't matter, and no element is listed more than once. Now, we've actually already used set notation when we describe sample spaces and events, so let's talk about them a little bit more formally. In list notation, which is what we've been using, we list the elements of the set separated by commas, and we enclose the entire list in braces. And we should also name the set. Typically, we identify a set with a capital letter. We don't often use it in probability, but it's helpful to introduce the following relationship between sets. If every element of some set A is also an element of B, we say that A is a subset of B, and we write it this way. You could also say that B is a superset of A and write this, but almost no one ever does. Note that since events consist of elements of the sample space, then every element of any event E is going to be an element of the sample space, so any event is a subset of the sample space. And again, mathematicians are not normal people. Since every element of S is an element of S, then S itself is a subset. We should also be specific about when two sets are equal. The obvious definition, which we'll use, is that A is B if A and B have the same elements. But let's be a little bit more careful. Note that this means that every element of A is also an element of B, so A is a subset of B. And every element of B is also an element of A, so B is a subset of A. So we can say that two sets are equal if they are both subsets of the other. So, given two sets A and B, the union of A and B, written this way, consists of all elements of A together with all elements of B with any duplicates removed. The intersection of A and B, written this way, consists of the elements that are in both sets. For example, we'll use list notation, so here A is our set consisting of the elements 1, 3, and 5, and B is the set consisting of the elements 4, 5, and 6. Then the union, A union B, is everything in A together with everything in B, but we have a duplicate, so we'll strike out that duplicate entry. Meanwhile, the intersection A intersect B, that consists of the elements that are in both sets, and the element that's in both is this element 5. Now, especially when dealing with intersections, it will be helpful to introduce a special set. The empty set is the set that contains no elements. And so we'll use our list notation. We give the empty set a name, and the symbol we typically use is this. And then we'll list all the elements of the set. Well, there aren't any. But of the elements that don't exist, we'll enclose them all in a set of braces. So our empty set might look something like this. So, for example, if our set X is the elements 1, 3, and 5, and our set Y is the elements 2, 4, and 6, then the union, everything in X, together with everything in Y, and there's no overlap, so we don't have to strike out any duplicates. Meanwhile, the intersection is the elements that are in both sets, and we find there is nothing in both sets. And again, we could represent the empty set using this symbol. If the intersection of two sets is the empty set, we say that the sets are disjoint, and these disjoint sets are going to become extremely important later on. There's another set operation that's useful. The complement of a set, designated either using a bar over the set name or superscripted C, is the set that contains everything not in X. Ordinarily, we'd need to define a universal set that includes everything, so we'd be able to define what isn't in X. For probability, our universal set is going to be the entire sample space. For example, suppose a 6-sided die is rolled and the number shown is recorded. Our sample space again consists of the values from 1 through 6, and we could define an event the number is even, just the even numbers, and the complementary event includes everything else, the numbers 1, 3, and 5.